Hi, everyone. Thank you for joining us today. Today we have Daniel Kifer. He's a professor at Penn State University. He received his PhD from Cornell. His work is focused on statistical privacy and its application in other fields such as software security, numerical optimization, and he's also interested in social science aspects of data. He is a collaborator with the U.S. Census Bureau, and he's serving on a committee for national statistics. So today he will talk about PerQuery Error and differential privacy. So without further ado, I invite Daniel to start this talk. Thank you.
Okay, thank you. Okay, so the overview of the talk is that when we create differentially private algorithms, we all have some commonly used measures of success that we're used to help us evaluate how well we're doing. So in this talk, I'm going to try to convince you that there are other measures we should also be looking at, and that interesting things can happen when we do. So to start, I'd like to acknowledge all of these wonderful and smart people that I have been working with. And without them, you'd be staring at 46 blank slides. So this talk is about the details. So here, sometimes details are details. In this case, details are important. So if something doesn't make sense or you forgot something, please interrupt and ask questions. I think the best talk is when you actually can't even get through all of the slides. All right, so let's begin. So first, there's a disclaimer. Because so many institutions are involved, I just want to point out that the views and opinions in this talk are my own. They don't represent any policy or official position of any agency, any company, or any university, and so on. So let's start with the basics. Right? So we're all working on formal privacy. Sometimes it helps to just take a step back and just see what we're doing. All right, so we have confidential data, we just can't release it. We want to create some public use data product, and so we use a formal privacy mechanism to convert this confidential data into something that we can use. So the formal privacy mechanism has to have a bunch of requirements. First, it's got to protect privacy. And the way we quantify privacy is based on this accumulated wisdom of the privacy community, which is now getting larger and larger.
The role of sort of expert regulations.
One wrong, can you mute everybody else?
Is that a question, or wasn't sure if someone had a question? Okay, so the privacy protections are quantified and formed basically by the math, by the wisdom of the privacy community, also by to some extent by policy and legislation. So it's like a two-way dialogue there. There's also a utility aspect, and this is or should be quantified by the accumulated wisdom of the stakeholders. So the people who will use the data, right? So there's a huge community of social scientists, economists. They know their analyses, they know how to measure errors, and basically they know how they like their steak. That's the way we should think about this. They're very particular. So the question is, what happens when we take a look at the kinds of Aerometrics that they're interested in and optimize for that? So that's the basis of the talk. So first, I'm going to spend a lot of time talking about the Aerometrics, how they differ from what we commonly use, because you just cannot emphasize this enough in order to get the rest of the talk to be understandable. Okay, so we're going to start off with some notation, and if you forget, I'm going to try to repeat it so there's redundancy in there. But we're starting with a confidential data set D, and you can think of an example would be the responses collected in a census survey. We have a set of queries Q, and this you can think of it as, okay, so census geography is divided into a hierarchy. The lowest levels are the blocks. So we might be interested in the number of people in each census block because that's what voting districts, school districts, and so on are created out of. We might also be interested in number of voting age people on the block, number of people in each race category, maybe at the block level, but also at the county level in different states, and so on. Okay, so we have confidential data set D, set of queries Q, and the individual query, just returning a scalar number, would be lowercase q. Okay, so when we apply a query to the data set, we get an answer. And so we're going to use this notation. And then we have a privacy mechanism. So we would like to get the answer to the query, but because of privacy concerns, we're going to have a mechanism giving us an approximate or a noisy answer. So this mechanism could just directly give us the noisy query answer. Like maybe it could compute the true answer, add noise to it, or maybe M could create a privacy protected, differentially private microdata, and then you can compute your own query answers from that. Okay, so there's a lot of flexibility in what M can do. And to distinguish that something is privacy protected, we add a tilde over it. So if our mechanism creates a data set that's privacy protected, it'll be D tilde. And if it directly produces query answers, it's A tilde. If we compute the query answers from the protected data set, it's still A tilde. Okay, so tilde means it's protected with differential privacy. So the metrics, there are two main types of metrics that are used in the existing literature. So people who are familiar with the matrix mechanism style work are commonly try to optimize total error. So we have, for all of the queries, we have the true answer, we have our privacy protected answer. We look at basically the sum squared, the expected sum squared error. And in the theory literature, we often see these kinds of error bounds, which are trying to say, what's the probability that all of the queries are accurately answered? So this, we want beta to be vanishingly small. And this alpha, this is like the upper bound on how big the error is for any of the queries that we're going to see. Okay, so another way to think of this is answering, is any single query far away from the true answer? Or how frequently are we going to see noise outliers that are going to make some queries just by chance inaccurate? So these are perfectly good error measures, but they don't capture the big picture. And so that's what I'm going to try to explain. So for total error, the nice thing about it is that you can create these elegant optimization algorithms that figure out what you need to add noise to in order to maximize the expected or minimize the expected error that you're going to see. So this is a kind of error measure that's most appropriate where all of your queries are used for the same application. Okay, but in practice, for example, in the Census Bureau, they publish a lot of statistics, and not everyone is interested in every single query. So some queries are used for redistricting, and these are queries at the block level, the lowest level of geography for which they publish any information. So blocks can be really small. And so if you know the number of people in each block, number of voting age people, you can start to put these together to form districts. But when you're talking about funding allocation, sometimes you're interested in larger geographies like counties. So if you're doing funding allocation, be more interested in getting accurate county level population statistics. And then if you're a demographer, you're actually also interested in distributions of males and females in different regions, typically counties, but it could depend on how populated those regions are. So in short, we have different stakeholders, and each stakeholder cares about their queries. They don't really care about the total queries or the total error. They just care about how the error affects what they want to do. So in this case, minimizing total error is not necessarily the right thing to do because it's not clear how to optimize the accuracy of individual queries. So some stakeholders might be okay with larger error on their queries, and some might need more accuracy on their queries. So there are modifications of this total error metric where you stick a weight in front of the error term. So you say, okay, for query Q, I'm going to weight it by W, which somehow means that larger errors here get higher penalties. So this is fine, but as I'm going to explain later, the relation between WQ and the final error that you get for the specific query, it's not obvious what this relation is. And in particular, if you set all of your weights to 1, that doesn't mean that all of your queries are going to be equally accurate. And we're going to see that it can be arbitrarily worse than that. Okay, so those are the limitations of total error. In terms of the simultaneous error, it solves some of those, but also leaves open additional questions. So again, this tail error is basically how good is every single privacy protected query answer that my mechanism is giving me. And this, I mean, the fact that this is useful is illustrated by how much studying this metric has led to a fundamental understanding of privacy trade-offs for different privacy definitions, different types of queries, and so on. In particular, it addresses the stakeholder concern that they only care about their specific queries, right? So this gives them an upper bound on how bad their specific queries could be. Okay. On the other hand, there's error is not just one thing. So error consists of many types of issues that lead to inaccuracies. So some examples are systematic error. For example, maybe a specific query is just going to be generally inaccurate. Or an outlier error. So maybe all of the queries tend to be accurate, but just because we have so many noisy answers, so many noisy queries, just by chance, some of them are going to be inaccurate. Right? So this is, just by bad luck, we're going to have some error. And this is not by bad luck. There's a systematic error that's happening in a particular query. Okay, so
So, do you have an example of what might cause a systematic error or where that might happen?
Yes, that's like half of the talk is about this. So let me introduce this at a simple level and try to get it more complex, and then we'll see if anyone gets lost, and hopefully not. Okay, so let's just examine first what just error due to bad luck or outlier error happens. So let's take a data set. So here's the data set. We're going to label the queries by their ID number. So let's say we have 10,000 queries, 0 or 1 through 10,000. We're going to get their true answers, just going to plot it like this. Right? So you can think of it, these are the true query answers. And suppose that they're disjoint queries, so we have parallel composition. So we can add Laplace noise to scale 1/epsilon to each of these noisy query answers. Right? And so what we're seeing is that, we have 1,000 queries. If you look at each individual query, right, it's within, with high probability, it's within plus or minus 4 epsilon of the true answer. So most of the queries are like in this kind of a band. And we see that, yes, there are 1,000 of them. So occasionally you're going to be unlucky. And so we have a handful of queries whose errors can be large. And these are approximately 2 log n over epsilon. So I'm plotting 99%. These are 99% confidence intervals. And so most queries for each individual query, 99% of the time, it's within plus or minus 4 epsilon. But when you have so many, just by chance, if you're going to be, within 2 log n over epsilon. And it's very unlikely that they're going to be larger than this. Okay, so this is just outlier error due to bad luck. But suppose instead we do this. So for the first query, we don't add Laplace 1 over epsilon noise, we add log n over epsilon noise. And for everything else, we add Laplace 1 over epsilon noise. So the error profile is going to be the same, right? So if we take a look at what is the probability that the largest error exceeds some bound, it's going to be the same as in this case, except the only difference is query 1 is going to be systematically bad, whereas in the previous case, some queries are going to be bad, it's like a lottery. Right? So this is what statisticians are very familiar with. You have a lot of random variables. Okay, some of them are going to be bad by chance, but here, some of them are going to be bad by chance, but also query 1 is always bad. Right, and then, so this is a little bit artificial. We'll see that this actually happens in practice. Okay, so just before then, let's summarize what we have. So total weighted error is great, but if you have individual stakeholders who only care about some of the queries, it's really hard to optimize for what they care about. And then simultaneous tail error is also great, but some systematic errors can get obscured by this Aerometric. Okay, so we need another thing to look at. So I'm not saying stop looking at them. These are good, but we need additional pieces of information. And this is something that we're calling fitness for use. So basically, or PerQuery error. Okay, so every query now has an error target. So the stakeholder says, I want this query to be this accurate. And the way we measure accuracy is we just look at this query. This query by itself takes its expected value. So we're not considering tail errors or the fact that we have lots of random variables. We're just looking at average behavior of this query, and we want the average error, average behavior of this query to be less than a stakeholder specified bound. So this is not, a perfect representation of what stakeholders would like, but this is closer than the other metrics. In particular, if you look at how census represents their data quality errors, like due to sampling error or other sources of uncertainty, they provide for each query a margin of error measure, which is basically a confidence interval created by a Gaussian distribution, which again is highly related to the variance. So there's, if you're providing unbiased query answers with a Gaussian error, margin of error is roughly equivalent to the variance of the query. So you specify a bound on the margin of error, it corresponds to a bound on the variance of the query. And so there are naturally two types of problems that this gives. So the first is accuracy first. So we want to design a mechanism that meets these requirements for every single query, and we basically maximize the privacy subject to all of these utility constraints. Okay, so basically all I did is we want this to be true, so we divide by CQ on both sides, and so that means for every query we want this to be less than or equal to 1. And then of course we have the privacy first. Instead of setting this to be the constraint, we can set this to be the objective function. We want to minimize it subject to the privacy constraints. Okay, and it turns out that if you're adding noise, you're doing additive noise mechanisms, these problems are isomorphic, meaning if you get an answer to this, you can convert it to an answer to this one, and vice versa. So this metric is what is studied in the two papers that I'm going to be discussing. So this one is going to appear in NeurIPS, and this one appeared at VLDB. This is also the kind of metric that was studied by Victor Balser and Salil Vedan. And in fact, it turns out that the same mathematics are causing the underlying problems. And what we're looking here are additional interpretations and consequences of the math. Okay, so just as a reminder, this is what we're looking at. Basically, the expected error of every query, and we put the max on the outside. So does any query have bad average case behavior? Most theory papers, what we're typically used to thinking of is like simultaneous tail error, and it's important to realize that we're not doing this. So we've seen a lot of results on here. They don't really imply anything about this, just because this is a lower bound on that. Okay, so this would be a good time to ask questions. And if not, we're going to see some real use cases where this obscures some systematic errors that this metric catches.
Dan, I have a question. So I guess another reasonable option would be to look at batch. Oh no, I guess this is the same. Sorry. Another reasonable option would be to look at average L2 error over sort of specific subsets of the queries. Like I want my county IDs, my county estimates to be on average, good to this. My block level, estimates to be on average good to such and such.
Yeah, that's so. Like I said, this is not the final metric that people should be looking at. This is closer to what stakeholders want. And of course, there are many additional metrics that are even closer, like what you propose. Yeah, so definitely true. And the point is that if you start examining these, you might notice new things. So for people who are looking for, let's say, a PhD thesis topic, the first half of this talk, we're going to see basically there's an open unsolved problem that really needs a solution, and it's pretty interesting and, in my opinion, also very difficult.
So one just follow up on that is that, and maybe this is for the end of the talk discussion or something, but what sort of work has there been on sort of more distributional notions of error? So that saying, like, not only do I want the average error to be small, but I want it to be kind of, I want the errors to have a roughly normal distribution or something like that, that says that they're kind of, you don't get like weird tail behavior or weird like uneven error behavior.
You mean in differential privacy or in like the other sciences that analyze the data?
No, I mean in differential privacy, like for differentially private query answering or data synthesis.
Yeah, so I'm not aware of anything that specifically focuses on this, but there's a lot of work that says here's the kind of noise distribution that the end users like, and so we're going to use that.
Right.
I think that's a, Gaussian noise is particularly a good motivator for this. All right. So quickly, what privacy? What I mean when I talk about privacy? It basically doesn't matter. We have results for all of these. But in particular, we're going to focus on what we can say about pure differential privacy and in the first part of the talk, and concentrated differential privacy, ZCDP more specifically, in the second part of the talk. This is the first time I'm giving a differential privacy talk without actually having the differential privacy equations on there. And I think really the only thing you need to know is that for pure differential privacy, this is the privacy parameter. The larger it is, the less privacy you have. And for concentrated differential privacy, this is the privacy parameter. The larger it is, the less privacy you have. The prototypical noise for pure DP is Laplace, and for concentrated, it's Gaussian. Okay, any questions? I'm assuming no. All right, so let's take a look at what happens in practice. Okay, so simple case, let's say we have a survey. We ask, what is your age? We collect the data. And we can collect the data and store it in multiple formats. The most obvious is it's a set of records, but the most convenient is to convert it to a histogram. Right, so we have this histogram X, X1 counts the number of 1-year-olds, X2 counts the number of 2-year-olds, and so on. So this is the kind of representation we're going to be mostly dealing with. It just allows linear algebra. Okay, so this histogram representation is equivalent to the microdata representation when the entries are non-negative and integers. So integers turns out to be not so much of a problem most of the time. Non-negativity is a much bigger issue. And we'll see why soon. Okay, so now let's suppose in this survey, our stakeholders are interested in two types of queries. The first is they want to know the total number of people. Right? This would be like if we're doing funding allocation of counties. And the second type of query are the individual point queries. So these are all disjoint, right? We have parallel composition. They cover different types of people. First is how many 1-year-olds do you have? Second is how many 2-year-olds do you have? Last one is how many 100-year-olds do you have? Okay, so the first one is the sum of all of those, and different stakeholders, would want this to be accurate, and some would want this to be accurate. Okay. So under pure differential privacy, right, the first thing we would think of is, well, let's take these true answers and add Laplace 2 over epsilon noise to them. So if we do this for every single query, we're going to achieve epsilon differential privacy. And the nice thing is we know the expected error of every single query. It's 8 over epsilon squared. All right, so nothing too controversial there. But there's always a question, can we do better than this? And we can if we notice that, let's suppose we're interested in the total number of people. We can estimate it in several ways. Well, we have a direct noisy estimate, right? Total number of people plus noise that is given to us by the mechanism. We can also take, noisy number of 1-year-olds, noisy number of 2-year-olds, up to noisy number of 100-year-olds, and add all of these up. So this gives us another estimate of the total number of people. This is independent of this. They're probably not going to be equal to each other because they're independent noisy things. And so we can combine them to get an even better estimate. So in fact, this is the best one we can do. We take a weighted average of these two estimates of the noisy number of people, and it's provably strictly better than either of these individually. We don't have to stop there. We can say noisy number of 1-year-olds is either, we either get a direct estimate by adding noise to the number of 1-year-olds, or we can also take noisy total people and subtract noisy other ages to get another estimate of noisy 1-year-olds. Again, it's independent. We can do weighted averaging and so on. Basically, we're using background knowledge. So we're using knowledge of linear equations between query answers to improve upon these original noisy measurements that we took. Okay, so the general structure here is we're going to try to estimate a histogram. So we have the noisy query answers. We're going to try to estimate a histogram. And basically, we want to minimize the squared error between the noisy answers that we got from direct measurement to what you would get from this histogram. So basically, we're trying to find a histogram that approximates these noisy query answers as closely as possible. And one of the most common approaches, because it's a very simple optimization problem, is just to minimize this total error between the histogram we're trying to create and the noisy answers that we got. Okay, and if you do this, then this is strictly better than just using the noisy estimates. Okay, so here's an example. Here's our histogram. This is the kind of data set we're going to be looking at a lot in this talk. So the blue is the true answer. So you can see for, so here we'll have query 1, how many 1-year-olds, 2-year-olds, so on up to 20. So we see that the number of 1-year-olds is around 50, everything else is 0. So when we add noise and then do this least squares solve from the previous slide, we get this red box. So this is where the noisy query answers are. And we see most of the time they're pretty close to where the true values are. And then sometimes, just because there's so many of them, we get something a bit larger. Okay, so the question is, can we do better than this? So we know that the true query answers, right, the true counts are never negative, but the things we get from OLS and just the noisy answers directly, they can be negative. So can we use this knowledge that our query answers really should be non-negative to improve the results? And so what we want to do is we want to find a vector, or like an estimate of our histogram that approximates the noisy measurements, these ones, but is also non-negative. Previously, it didn't matter, but now we just want to make it non-negative. So what we're doing is we're changing our optimization problem from ordinary least squares, which would be just this part, to non-negative least squares, where we require our estimated histogram to produce non-noisy, to be non-negative. Okay, so I'm going to call this NNLS post-processing to distinguish it from ordinary least squares. So the only difference is we want to make sure that the histogram that we get from post-processing is non-negative. And once we get this non-negative histogram, we can start using it to answer queries. And if it's a counting query, again, it's guaranteed to be non-negative. So intuitively, we're adding knowledge, additional knowledge into this post-processed query answer. So hopefully our error will improve again. And so the question is that true? So with ordinary least squares, we can prove that if you do this ordinary least squares post-processing, the noisy estimates that you get from the histogram that you obtain is always better than the original noisy measurements. And this is actually just a direct application of the Gauss-Markov theorem. So does the same hold true when we add even more background knowledge that the fact that the query answer, the histogram should be non-negative? And this is what you can observe. So we took our the data set where there are 51-year-olds, or actually this is slightly different. So we have the first query, like one disjoint subset of the population, let's say 1-year-olds, has a lot of people in it, and everything else has 0. So we add noise to all of these query answers. We post-process using either ordinary least squares or non-negative least squares. And then taking this post-process histogram, we compute answers to the sum query in each of these individual queries. And then we measure the error. Okay, so what you're seeing here is the errors. So for ordinary least squares, the error is the same, whether you're looking at the sum query or looking at individual point queries. It's about 8 over epsilon squared. It's the same. For an NLS, if we look at the expected error of each query, so the ones that are 0, which would be 2 through 100, their errors are really tiny on average. Okay, so a lot of queries, their error goes from all the way here, all the way down to here. But some queries become really bad. So number of 1-year-olds, instead of its error being, like OLS error, it just skyrockets. It shoots up quite a bit. And also, if you want to estimate the total number of people, that also shoots up quite a bit. So this is not tail error. This is the average error of the sum query when you just consider by itself. And this is the average error of query 1. So these two queries have systematically high error under the NNLS approach. And these queries are really, really great under the NNLS approach. So some things improve, some things get worse. If you look at the total error decreases. So that hides the fact that we have systematic errors. And if you look at tail error, that actually also hides the fact that we have systematic errors, because these match the simultaneous error bounds. Okay, but they're, it's simultaneous error bounds look for whether any query, whether it's due to random chance or due to systematic error, are large, but these are always large. Okay, so this would be a good time to revisit the question of when do we see systematic errors in practice?
And can you
or did this resolve?
Just say, can you say again, what is the data set summarize again, what's the data set here? So Q1 is the number of 1-year-olds, and the data set is
so you can think of so basically we went to a daycare, we got a whole bunch of data on 1-year-olds, right? And there's no one else there. So there are roughly, let's say 500, roughly 50 people in here. So it's actually the same data set here. Right, so the 51-year-olds, nothing in the other age groups. Right, so this is a very sparse data set.
Okay. And the point is, if you didn't do the post-processing, or if you did OLS post-processing, all your errors would be, roughly similar.
Yeah, roughly here.
Right. But like specifically what's going on, just so I just make sure I understand the example, so that, post-processing for non-negativity will generally push up the estimates for all the other age groups, and that will lead us to push up the estimate of the sum. Is that right? Sort of trying to figure out what.
Yeah. Well, so the idea. Yeah. So the idea. Well, with NMLS, it's a bit tricky, but the point is, so this is not. Right now, we're not showing the consequences of non-negativity. We're showing the consequences of using NNLS specifically to enforce non-negativity. And with NNLS will.
But
okay.
That actually doing.
Yeah,
Maybe it doesn't matter that much. It's fine if you don't want to spend time. I don't want to slow you down too much, just for the details of the. Okay.
All right. I think what for now is important is that NNLS makes some things better, especially if they're near 0, but other things could get significantly worse, like the error on the sum query, the error on specific queries can become systematically bad. It's not just random, but these ones will always be bad. And it depends on the input data set, right? So in some input data sets, you get something really bad systematically, and in some cases, it improves. But the systematically bad error happens on sparse data sets like this one. Okay, so basically the main idea is that, like I said, many query answers become very accurate, especially the ones near 0, but some get large systematic error. And in this toy example, the two queries whose PerQuery error was large, meaning they have systematically large error, is the total number of people and the number of 1-year-olds. In particular, we did post-processing. We took noisy answers and then we did some post-processing. So these answers are much less accurate for these two queries, much less accurate than the noisy measurements we started out with. And it's a little bit counterintuitive, like we're taking the noisy measurements, trying to pull everything together, and we ended up with answers that are worse than what we started with. And this happens specifically because of non-negativity and NLS. It's not due to privacy budget allocation. Every single query got the same privacy budget. This is specifically due to our attempt here to deal with non-negativity or to use that as some kind of knowledge. And so the question here is, well, is this a pathological example? Or maybe it's not, but having a lot of these queries becoming so much more accurate, this is better than, it outweighs the larger error on these two queries. And the third question is, if not, is this kind of error avoidable? So real life example. By now you know the 2020 disclosure avoidance system is using differential privacy. It was applied to historical 2010 data, and there are a bunch of demonstration products released using different versions of the algorithm at different privacy budgets. And the goal there is, to get feedback to see where improvements are needed. And the rough overview of how it works, this is much, much more complicated than this, but this is how it started. So we pick some queries, get their answers, add noise to them, and then we want to create microdata, tilde D, so that if you compute your queries from this microdata, you get back something close to those noisy answers. That was the goal. And the main tool there was using non-negative squares, like we just tried, plus rounding. The rounding is also interesting, but it's not, doesn't drive error as much as this non-negatively squares did. So in these data demonstration products, they were analyzed at a CNStat workshop. And what was noticed there is that often, the query answers from the microdata are more accurate than the noisy measurements. So in other words, you compute the query answer from this post-processed microdata, it's closer to the true value than the original things that we added, than the true value plus noise. But sometimes for some queries, the error was systematically larger. So much larger than the standard deviation of the noise. So basically, what they observed was this kind of phenomenon, but in a real setting. Right, not a toy example, but a real setting where some queries are much more accurate. Others, the error is so much larger than the standard deviation of the noise. Right, and of course, so it's not a pathological example. And the question is, well, fine, but is this a good trade-off? That some are much more accurate and some are worse? And again, the answer here is no, because we have different stakeholders, right? So people who are interested in individual point queries, okay, for them this might be okay, but for people who are looking at aggregate statistics like funding allocations, having huge errors there, not due to privacy budget allocation, but just due to post-processing, that would be unacceptable, right? Some people, their queries become systematically bad, and so accuracy on those other queries they don't care about does not outweigh this. So finally, and then finally, we're going to ask, so is this problem avoidable? So it's not pathological. People are going to get mad if it's there. Can we avoid it? In particular, maybe we shouldn't take noisy measurements and then post-processing using non-negative squares. Maybe there's some really clever microdata algorithm that can fix this problem. So it turns out, yes?
So what solution space we're looking for? So we're looking for like one post-processing. So in some sense that like the way you formulated the question so far, it's about sort of post-processing a set of queries, right?
Yeah, and so the question is, was that a bad idea? Maybe forget about noisy measurements plus post-processing. Let's take any differentially private algorithm that takes microdata as input and produces microdata as output. Right?
Well,
maybe
actually,
there's a clever algorithm.
I was going to go somewhere slightly different, which is to say, like, maybe what I want is different microdata for different applications, or like different post-processing for different users?
Yeah, okay, this is a great question. We can dive into it at the end, but
Good,
this
fine.
would be a non-starter for census applications because you'd have different official estimates, and people be confused about, okay, I have different microdata. For some queries, they'll give me different answers. What do I do? So yeah, this would be right. So we're kind of living in a constrained situation where we just our solution space is restricted. Right? We have to produce one microdata set, but we can choose the algorithm that we want to use.
Thanks.
And it turns out, clever algorithm can help. It can partially avoid these mistakes. Basically, some data sets, it can avoid large errors, but there's actually an uncertainty principle, meaning that for some data sets, there's just nothing you can do, no matter how clever you are. Okay, and so this is the main idea of the uncertainty principle. So we have these disjoint point queries. You can think of it as like the number of people in n different categories, and we have the sum query, total number of people. So this is a kind of pattern that happens a lot of times, like almost every single census tabulation has this kind of pattern in it, where we break down people into disjoint categories, and we also tell you how many people they are. For example, we can look at point queries, number of people in each block inside LA County, which again, useful for redistricting. The sum query would be the total population in LA County, and that would be for funding allocation. Or you can think of like this may be number of Hispanic people in each block in LA County, and this would be the total number of Hispanic people in LA County. Okay, so different types of queries. The individual ones are useful, their sum is useful, but they're for different applications. Okay, so you can choose what DP algorithm you use, but you have to produce microdata. And it turns out that you kind of like have a Sophie's choice type situation, where you can either guarantee that all of these individual queries have expected error 1 over epsilon squared each. Right? So not simultaneous error, but each one has this expected error profile. But if you, oops, okay, sorry, I swapped these two. You can either guarantee that the sum query, like total number of people in LA, has relatively small error, like 1 over epsilon squared. Same thing that you can do with just adding noise. But the point queries may have error up to log squared and over epsilon squared. So this is not tail error. This is some query, a specific query, which depends on your data set, could have an error, expected error this big. Okay, so this is why I spent all this time explaining that PerQuery error is different from simultaneous error. So simultaneous error will hide the fact that some query, specific query, is going to be this bad. If you look at PerQuery error, there are queries that are going to be systematically bad if you have a sparse input data set. So if you want to avoid this, you can. So maybe we can make the sum query less accurate and push down on the systematic error in these individual queries. And you can do that. So you can guarantee that the point queries each have expected error 1 over epsilon squared instead of some being systematically bad. But in order to do this, you can't guarantee that your sum is any more accurate than this. In other words, you might face a blow up of n squared. N is the number of things that you're adding up. N squared, it would be the blow up if you want to guarantee that each individual query has expected error on average that looks like this.
Dan, can I ask?
So, and then yeah.
I mean, I can save it for the end of the slide when you're, but.
I'm pretty much done. I just also want to point out that there's really nothing in between. It's either this or this.
All right. So my question was sort of like, what's the class of DP algorithms that you're restricting to? So you're restricting, is it the case that you're restricting to estimates that are kind of produced by generating like a synthetic data set that's like is the one thing you can do is add Laplace noise or Gaussian noise to all of these queries and just not do any post processing, and then I think you get away from this problem, right? But
yeah,
like,
exactly.
the issue is coming from like some notion of like consistency with a single non-negative histogram or something like that. Is that?
Yeah. So the point is, if you are required to produce, so input is a histogram. If you're required to produce a histogram as well, and maybe even you can have fractions in there, but you cannot have any negative numbers, then no matter what algorithm you use, you're going to have this error.
Okay.
You're going to have this trade-off.
Yeah, thanks. That's, and it's a completely reasonable, I mean, that is, there are many situations where that requirement is like in place, like for example, for the census. So.
Yeah, and in fact, the census made this requirement. At the time, it didn't seem like such a big deal. After years of development, we're seeing, okay, even things that seem like small decisions actually can have consequences. In fact, we thought that this would be better, right? Because you take advantage of the fact that queries are non-negative and so on. So on average, yes, things do improve, but there are some queries that become systematically bad. And it's kind of like a trade-off. You will try to push down on the systematic error in some queries, it pops up in other queries. And so this was the upcoming NeurIPS paper, and I want to point out we have results for concentrated differential privacy, approximate differential privacy. They all have this type of choice that you would have to make. Okay. So
I have a question about what restrictions do we have on the point queries? Can I have a point query that's like the population in all census blocks except one in LA County?
Yeah, so these have to be disjoint.
Okay.
So these would be
okay.
Yeah, these would be things that you can apply parallel composition to, and this is the total. So sensitivity is not really an issue. It's not a factor. It's not the allocation of privacy budget that you might want to do between these. It's really the fact that there's non-negativity means that you have to make a choice about where you want the systematic error to be. And in some cases, it doesn't look very good at all.
Cool, thanks.
Okay. So there's good news, and that this kind of uncertainty principle is not triggered for all data sets. It's really triggered for data sets where there's something large and a whole bunch of zeros. And so even if let's say I know that one of them is 50, I just don't know which one it is. And I know all the rest are zeros, right? To get, all of these accurate, to get this accurate, and to get the sum accurate, basically I need to identify which one is the 50 and which one are the zeros. And that's actually hard to do for like when this is approximately log n over epsilon. And these are all zero. That's where the problem comes. If this is much larger, you can avoid this. When this is much smaller, of course, you can also avoid this error. So it's specific data sets, but they do pop up in practice. Okay, so questions, what can we do? There are basically two approaches. So the first is, okay, don't create microdata. So we relax things. In particular, we could relax the non-negativity assumption. So if we can create, instead of these histograms, we can create maybe some kind of a more general synopsis that sometimes gives us negative answers to queries, then we can avoid the situation. So maybe we just release noisy measurements, or maybe we make the microdata weighted so that a record can have negative weights, and then you answer a query by taking the records that satisfy your conditions and adding up the weights. So this is good. But if you actually then add the fact that you want a sparse data set that is weighted, then you go back to error results produced by Balser and Vadan, which shows that, again, sparsity causes systematic errors. Okay, so the nice thing about this is this approach is you avoid, you can avoid the systematic error trade-offs, and all the end users are going to have to confront the fact that their data is uncertain. So they didn't do it in 2010. There was data swapping being used, but it was kind of hidden under the rug for most people, and so they weren't very upset about it. With differential privacy, we're saying, yes, we're adding the noise, and we're going to tell you exactly how. It's in their face. They start getting upset. Okay, but in fact, in all cases, they should be confronting uncertainty in the data, and by not creating an output that just looks like data, by creating an output that looks like noisy data, right, or particular, has negative numbers, has fractions, then they know this is not the same as the ground truth. We had to add noise to protect confidentiality, to basically make people more willing to provide their true answers to the census. So there's a conceptual benefit to this. But post-processing does improve error on some queries. So maybe there's a post-processing algorithm that is something like instance optimal. So for some data sets, you avoid this trade-off. And for some, like the ones that I showed, it's unavoidable. Okay, so there's the error. And maybe we can identify, okay, on this particular data set, these are the queries that you couldn't really trust. Maybe we can release the noisy measurements for those queries. Okay, so if we don't drop the non-negativity and we try to use it to improve accuracy, we do improve on many queries if we can identify where actually we are making the large errors and kind of having instance optimal algorithms. That would be the best thing, or a really good thing. Okay, so this is kind of the direction taken by the Census Bureau because they committed to producing microdata. So we had the non-negativity requirement. And so like 99% of the engineering effort, I'd like to say, is spent because of this non-negativity, trying to mitigate systematic errors. So there's been a lot of work there. So paper detailing all of these is not yet available, but I would imagine it would be at some point. Okay, so the amount of effort put into solving the system, there's some simpler alternatives or simplifications of it that we presented, that we put into our NeurIPS paper. But I think one of the nice things to get out of it is that we have toy data sets that sometimes trigger and sometimes don't necessarily trigger this uncertainty principle. We have some code that you can evaluate with them. So toy data sets plus code. And the idea is you want to avoid being really bad on absolutely all of the data sets. So it's very easy to get an algorithm that is good on some data sets, really bad on others, but we want to just avoid being really bad all the time. So sometimes maybe we're worse than OLS, but not significantly worse. And then a final note, what we've noticed is with differential privacy, a lot of times optimizers, like solving for NNLS or more complicated objectives, they're not very good. Even on our toy problems, we had to experiment a lot to find a decent open source optimizer. So Gurobi is really good, but it's commercial. It can solve these problems. When you go into larger scales, again, even then, you can start testing the limits of Gurobi. But the point is, optimizers exist, they're good, but they don't solve our problems very well. And so two really good research directions to try to solve this instance optimal non-negativity issue, and while also creating good optimizers for the types of problems that arise in differential privacy. Okay, so then we have a little bit of time to talk about, well, suppose, okay, we accept the fact that PerQuery Error is useful for end users. Is there a way we can optimize for it? So can we design algorithms that we figure out what kind of queries we want to add noise to? Maybe we accept negative answers, and we want to add noise in such a way that we meet our error targets for each query.
Daniel?
Yes?
It's 12 o'clock here, and I think it's officially the end of the talk. We will be happy to stay longer, but I just want to say if people have to leave, just give them the opportunity to
Right.
Okay,
right,
so
yeah.
let me just point to two
People who have
papers and then I'll be done.
If there are people who have to leave at noon, maybe they can, give them a chance to ask questions, and then you keep going for a little bit. Like, we're happy to. I in particular would love to hear this last part of the talk.
Okay. All right, but before people leave, 30 seconds.
Sure.
So this work is in our VLDB paper, so if you're interested and have to leave. And there's another thing I want to talk about, but we have an upcoming CCS paper. We have two students on the job market, one on the internship market, and the kind of problem they're considering is how to replace us all with machines. So we take an ordinary program and a utility metric, we do some magic using programming languages techniques, create a differentially private program out of it that is tuned to specific utility metrics. And this program can actually do interesting things like dynamically track its privacy budget and make decisions based on that. Okay, so That's it. And then for people who want to listen to the rest, we can go back.
Any questions? Okay, so let's continue. Sorry for the interruption.
Okay, all right. So hopefully by now I've convinced you that looking at in expected error of individual queries is useful and provides interesting insights, right? So just looking at the simultaneous error does not give you a complete picture. Okay, and so if we look at this PerQuery error, fitness for use requirements are basically constraints on the accuracy expected error of each individual query. So we know that if we try to make the query answers non-negative, if we want to force that, that can have undesired side effects. It leads to an open problem. Hopefully someone can solve it in the near future. But until then, let's think about what happens if we drop this non-negativity requirement. So can we figure out what kind of queries we need to add noise to so that the stakeholder queries meet their accuracy targets? Okay, so another good thing, not captured by an error metric, but are just properties of these noisy answers. So if the answers are unbiased, if they use Gaussian noise, they add another level of usability for stakeholders. They can form confidence intervals. It's easier for them to do hypothesis testing. Their statistics, the way they do statistics doesn't have to change too much, right? There's a lot of theory that they can draw on. So here, now we're into like the kind of framework set up by the matrix mechanism. Our data set is a histogram. Basically, for every type of person, you have an entry in the histogram. So you can say like X1 is the number of people who are not adults, not Hispanic. X2 is the number of people who are adults, but not Hispanic, and so on. So all combinations of records are represented here. And so X is just a count of how many people of each type are there in our data set. So a query is just a dot product between this and some weight vector. Usually the most interesting ones are queries where the weights are ones or zeros. So like this. So we have a query matrix. Every row corresponds to a query. And so to answer that particular query, we would take this vector, dot product it with this vector to get our answer. So for example, this query represents the number of people who are adult, right? We're adding up this and this part of the data. This one would be the number of people who are Hispanic, and this is just the total number of people. Okay, so we have data set as a histogram, queries are vectors, take that product. A set of queries is just a matrix. Okay, so for convenience, and this is for computational convenience, we're going to take our query matrix, the one that stakeholders are interested in, and we're going to factor it. And however we factor it doesn't matter too much. It might affect the computational cost of what we're going to do later, but it doesn't matter. Like you might set one of these to be Q, the other to the identity. If you don't like factoring, if you do like factoring, you can do it this way. Okay, so our mechanism is basically, so B is the set of queries we're going to add noise to. So we're going to compute the true answers, BX. We're going to add correlated Gaussian noise to them. And then we're going to multiply by L to get estimates for what the stakeholders care about. Okay, so we add noise to these queries, and then we reconstruct what the stakeholders want by matrix multiplication. So so this is a very similar setup to a matrix mechanism or factorization mechanism, if you're familiar with these works. If not, the references are here, and I encourage you to take a look at those. Okay, so this is kind of a standard thing. What you want the answers to is not what you're adding noise to. You add noise to something else, and then you figure out the answers. Okay, so our goal is to figure out, so the factorization you choose for computational convenience, our goal is to figure out what is this correlated Gaussian noise you should be adding to maximize your privacy while meeting the accuracy targets. Okay, so the stakeholders for every query, for every row in your query matrix, they tell you we want the variance to be at most CI. So before we took a look at this problem, the most common approach was to solve it using the matrix mechanism. So we choose how we add noise by optimizing the total error. So we don't directly do this, but we optimize the total error. And then we see what kind of variances we get, and we rescale the entire noise vector, the entire covariance matrix. We rescale it so that the variance constraints are met. So we optimize this to figure out how much of the privacy budget is associated with each query, and then we rescale it to meet the accuracy constraints. That's the traditional approach. So it turns out this can be suboptimal, and we worked out an example where the suboptimality can be arbitrarily large. So let's take a look at this familiar example. We have a county. It's divided into D regions. So as before, we want to estimate the total county population, and let's say variance target 1. And for each region, each of these disjoint regions, we also want to estimate their population with variance 1. So it's the same setup as before, point query and the sum query. And it turns out that this one is also shows some interesting results. So this is kind of like a good type of query to study. So this is what happens. So here we're measuring to achieve this variance of 1 for the point query, for each individual point query and for the sum query. Right, you can use the matrix mechanism approach to try to figure out how much noise to add. And then you can measure, if you add Gaussian noise, you can measure the privacy cost in terms of rho for ZCDP. And then you can take a look at, well, what is the optimal way of doing it? And we measure the privacy cost. So what I'm showing you here is the ratio of using the matrix mechanism, which optimized for total error. So this is how much extra rho you need in order to achieve the target metrics compared to the optimal solution. So as your number of subregions grows, it's kind of like a square root of D. So D would be the number of regions. So this, the privacy loss ratio, how much extra privacy budget you're spending unnecessarily increases roughly as square root of D. Okay, so for this example, we actually have exact analytical results for what the solution looks like.
And can you repeat what the optimum is, just so?
Yeah, the optimum is basically solving this problem. So I want to minimize privacy costs such that all the variance constraints are met. Privacy cost is basically here, this is 2 times the rho parameter from ZCDP. So if I directly solve this, minimize the rho parameter in ZCDP such that all the variance targets are met, right? That's the optimal solution. And the approximate solution,
Is taking B is fixed? I'm still trying to parse the.
Okay. Yeah, so there are many equivalent ways of doing this. So matrix mechanism, makes this identity and makes this something that you optimize for. And this would be a pseudo inverse. Factorization mechanism takes this identity and optimizes over all choices of L and B. I mean, they're all mathematically equivalent as mechanisms. What we're doing is we're fixing these two. Like maybe you can think of B as Q and L as I, or however you want to do this. But we're figuring out, okay, here's what you want to add noise to. Here's, we figure out what kind of correlated noise to add. And then you get the stakeholder queries from it.
I guess one of the things that confused me, but maybe it's not that important, is like if I'm searching over all possible sigmas, why do I need both L and B? Is it like?
It's just for computational reasons. Sometimes, basically, it's an optimization problem, and you've got to do linear algebra. And sometimes, if you factor it in the right way, you can solve it faster.
I see. Okay. Yeah. Thanks. That makes sense.
So basically, we can do a direct optimization. You don't have to use the matrix mechanism. You can do it this way. And while this looks, for some people, this looks lovely. For other people, it's just too many symbols right away. But basically, this is exactly equal to the rho ZCDP privacy cost. And these are the variance constraints. And of course, the noise has to be positive semi-definite. So it's an optimization problem.
What's the maximization over?
So the maximization is over the diagonals of this.
Okay.
Right. So it's basically we do some linear algebra. It gives us a vector. We take the worst thing in that vector. That's the ZCDP privacy cost.
Thanks.
Yeah. So like this entire thing is the rho. Okay. So if you look at Alexander Nikolov's PhD thesis, this optimization problem is actually very related to something he called computing the ellipsoid infinity norm. And what's interesting is we're looking at this PerQuery error and trying to optimize for it. He was looking at simultaneous error and also in some cases total error. And the end result is that this optimization problem pops up in both places, showing that it's kind of important. All right. The next observation we can get from looking at this math is that, okay, so we have this vector operation and we're taking the max. And whenever we take a max, right, we can have ties and so on. Max functions are not strictly convex. Right. So in this case, that means whenever you have a max and trying to minimize the max, you can have multiple solutions. And turns out that this is no different. You can have multiple solutions, but there actually exists a uniqueness property. There exists a unique solution that has the best privacy among all row ZCDP mechanisms. And this, we can get this by taking a look at something called personalized differential privacy. So personalized differential privacy looks at more fine-grained. Basically, the idea is, let's suppose I have a data set and I'm only asking queries about people who are over 18 years old. Right? I'm asking 0 queries about people who are under 18. So you can think of intuitively, if you're 18 or over, whether you're in or not in the data set, your privacy is protected by some number. But for people who are under 18, since no queries are being asked about them, whether you're in or out of the data set, like it doesn't matter, right? Because you don't affect the answer at all. So depending on what your true value is, you might be getting better privacy from a particular mechanism. And so you can generalize this to, you have a privacy parameter for each domain element. The largest of those would be your row from row ZCDP, but specific combinations of specific domain elements can have larger privacy, right? So privacy is unequal here. So it turns out that if you measure privacy this way, you get a partial order over privacy mechanisms. And so this partial order, it has lots of minimal, lots of minimal things, right? Because it's a partial order. But when you combine this partial order due to personalized differential privacy and this max optimization, it turns out that there's a unique solution that is, so basically out of all the solutions to this, there's a unique solution that dominates all of them when you measure privacy by personalized differential privacy. Like they have the same overall row, and you break ties by seeing, which one has a better personalized privacy. It turns out that there's a unique best which dominates all of those. So that was kind of a surprising thing. And then the final observation is, this is a semi-definite programming problem. There's a lot of literature on this, but algorithms for the kinds of problems we have in differential privacy, the kinds of things we want to optimize for, these solvers are just not very good at it, especially the open source solvers. And so frequently, we have to create custom algorithms for it. So in this case, we created a custom approximate conjugate gradient descent algorithm that took specific characteristics of this and basically gives you a near optimal solution. So some experiments just to see, we showed you one example where optimal solution could be very far away from what the matrix mechanism gives you. But let's take a look at some examples inspired by real world query workloads. So the first one is PL94-ish. So I call it PL94-ish because it's not exactly the requirements used for redistricting queries, but it's close enough. So in this case, we have 3 kinds of variables we're interested in. So there's whether someone is voting age or not, the race combinations that they have, which have 63 possible values, and then whether they're Hispanic or not. And the types of queries that are interesting, which closely mirror what the PL94 publications from Census provide, not identical, but closely mirror, is, okay, you're interested in the identity query. So for each type of race, ethnicity, and voting age combination, how many people there are, and then each one-way marginal. How many voting age people are there? how many people of each race combination, and so on. Okay, so let's suppose, so we're not going to put our thumbs on the scale. We're just going to say every query we want to be equally accurate. And then we can see, all right, if you solve the optimal problem, right, how much row do you need? Or, yeah, how much row do you need? And then if we give that same amount of row to, let's say, input perturbation or the metrics mechanism, by how much will they exceed the variance requirements for the query? Like, by how much will some query exceed the total variance of 1? So input perturbation, predictably not so good. Matrix mechanism is okay, but you can think of it as either to meet the targets, matrix mechanism or style approach where you solve that and rescale, will need 4 times as much row, or equivalently, some queries just going to have an average error that's 4 times larger than what you want it to have. We have another example useful that demographers care about are age pyramids. Here I forgot the one. So the ages from 0 to 115. And then there's also gender categories. In 2010, it was binary, you're either male or female according to census. So basically 200, roughly 200, the histogram, roughly 200 cells in it. And so the queries that we're interested in is prefix queries. So how many people are from 0 to 1, 0 to 2, 0 to 3, 0 to 4, and so on. For overall population for female cells. And we also want to know how many voting age people, 18 and higher. So again, if we set the target variance to be 1, we see, okay, input perturbation is not so good. Matrix mechanism is actually not that bad. It's like 1.5 times worse than optimal. And of course, our approach gives the pretty much the optimal solution to it. All right, so I know I'm standing between you and lunch, so that's not true anymore. I just want to highlight that we have a cool CCS paper. And yeah, so I'm ready for any further questions.
So I had a question, maybe returning to our earlier exchange about multiple post-processing choices, which is, I appreciate that there are settings where it's unreasonable to think that there could be multiple, that different post-processings would be used for different applications because there's only one official set of numbers, and telling people that there's more than one would make their heads explode or whatever. But there are certainly other situations where it is reasonable, and that, I'm thinking specifically of settings where the people who are using the data are more sophisticated, are like scientists who are doing research as opposed to people constrained by kind of legally sticking to the official numbers. And there you could, one might imagine that like, then what I'd be optimizing for would be like, I want to release something that many people could, for which there are like multiple good post-processings, right? Sort of like different matrices. I want one choice of B and sigma because that there's only one of, because it's like nailed down and there's a release. But then there could be many matrices L, or not just linear post-processings, but other types of things, consistency, non-negativity, whatever. And I wonder if there's like a meaningful version where you sort of optimize for multiple different things that people could choose to do later, like optimize for simultaneously optimize for multiple downstream uses.
Yeah, so that's kind of like what we're trying to do with this fitness for use, right? We have a bunch of downstream users. From each one, we force them to tell us what's the variance, maximum variance they want for their queries. Now, of course, variance is not always the right thing to measure, but we have to make a cow spherical in some way, right? So we get those, and so it's not always clear what you should do, right? But if they do want these variance constraints to be met, we can solve theoretically this optimization problem, create noisy measurements, right? If they wanted unbiased Gaussian estimates. And then for their specific application, they can try to post-process however they want. So that's, it's perfectly good. And that's kind of like this first approach where you forget about creating this one data set, non-negative data set for everyone. Just give something that, maybe it does not look like data, but they can post-process in whatever way they want to create their, to do their downstream task.
Right.
Yeah, and then this would be, even if you have a downstream task, but it has a lot of queries in it, and maybe you're interested in details and overall aggregates. So again, you'd have to do some kind of post-processing, maybe with non-negativity, and then you'll run into this situation again.
Yeah, so I guess what I was asking, if the optimization framework could accommodate like the existence of multiple matrices L, for different downstream uses. It's not, so I guess when everything's linear, it probably doesn't matter that much. I suspect that, like, it may not change that much. It's when it's like these projection steps that
Right.
things get complicated.
Yeah, in fact, linear and unbiased are kind of good properties because, if someone wants to add up a bunch of unbiased things, you get an unbiased thing and you can predict what the error will be. But if you add up a bunch of biased estimates, all bets are off.
Yeah. All right, thanks. Other questions?
Okay, so I just want to point out, we have code, we have data sets. It'd be great for someone to solve this problem.
Cool.
Right, so let's thank Daniel one more time.
All right. Well, Dan, you can't join us for lunch, but you can take a rain check if you want anytime you do happen.
Thank you.
You're more than welcome to drop by. All right.
Thank you. Have a
Okay.
good
See ya. Thanks again for the talk.
Bye, everyone.
Thanks a lot.